Okay, so folks, welcome. Happy Thursday afternoon. We're almost done. Here's what we're going to do today. We're going to just keep doing one of those examples we did before on Tuesday. So I'm going to kind of walk through another example. So what I want to do is kind of show you where we're working from. Here's the deal. I'm going to have the chat up, so feel free to use the chat and ask me questions. I can see the questions coming up there. If you want to talk and turn on your mic, feel free. That's perfectly fine. Hang on. Okay. Okay. So what we're going to do today is we're going to do a two-sample sampling distribution for proportions. So what I want to do is I want to go ahead and show you what we got. Make sure you all see the screen. You all see our Schoology page. Making sure.
Yeah.
Well, thank you. I just need to make sure, that's all. Okay, so we're in this folder, Virtual Day. That's where we are. So everything I'm going to be doing is in here in this Virtual Day folder. I'm going to do this example. What I am going to do is then there's a practice and an answer key that I'm going to give you that you can kind of work on over the next 5 days just to kind of get your head around this. What we were originally scheduled to do today was get started on sampling distributions for means. We're going to push that off until Wednesday. What I'm going to do is instead of doing 2 days on it, I'm going to do 1 day on it because realistically, it's very, very similar to what we're doing right now. So I was just going to kind of space it out a little bit. I'm just going to condense it just to make up some time. We're going to see it a lot. So I'm going to work this example. This example is going to be a two-sample sampling distribution for proportions. So what we did last week, so last week at this time, when y'all were doing the Reese's Pieces thing, we did a one sample sampling distribution. And what we did was the following. We actually looked at sampling distribution for one sample proportion. So what we said is we needed to know what proportion of these Reese's Pieces were orange. So what we did is we went and we took 50 Reese's Pieces, we counted the orange ones, and that gave us a p hat. So what we wanted to do with that p hat is we wanted to do that p hat over and over and over again. And what happens is if we start sticking them on a number line, they start to form a distribution. It's called a sampling distribution. These are all different individual samples. Each one is a different group of 50 Reese's Pieces. So what we did last week was we are, as with every distribution, we want to look at the center, we want to look at the spread, and we want to look at the shape of a distribution. We want to look at the center, the spread, and the shape of a distribution. And the way we do this is as follows. Our goal is always to get this thing down at the bottom if we can. We want a normal distribution. Because if a distribution is normally distributed, and I know the mean and I know the standard deviation, I can use normal CDF. I can use table A to figure out areas under the curve. I can go ahead and do that. So let me kind of walk through again what that was. What that was as follows. To figure out center, that's the idea of understanding if something is an unbiased estimator. So it's the center of the bullseye, that bullseye chart I had up on the screen. So the way I figured that out is I determined if things were randomly selected or randomly assigned. So what I mean by that with randomly selected and randomly assigned is somehow the process has to be random. That's the best we can do. If we do something randomly, we can then say we have an unbiased estimator. And if we can do that, then what we can also say is the following. We can say that the average of all these little p hats will be centered at the real answer. So if I kept taking those samples of 50 Reese's Pieces over and over and over again, and I did it thousands of times, and I took the average of those thousands of times, that would narrow me on to what the real answer is. So the mean of a sampling distribution is centered at the true mean. That's our goal. And the way we do that is by random. So questions on that from last week, actually. Okay, I'm just making sure because people type, so I give it a few extra beats. The next thing we're going to figure out is spread. Spread is standard deviation. Spread is variability. And that was that new thing I taught you, that 10N rule. The 10N rule is the thing we're going to have to validate moving forward to confirm that we're taking a sample size that is not too large. In other words, what I'm saying is We need to look at whatever our sample size is. We need to multiply it by 10. We need to compare it to what we know the idea of the population is. So with Reese's Pieces, we had 50 of them. 50 times 10 is 500. It's safe to assume there are more than 500 Reese's Pieces in the world. So we're not violating independence. So if we actually abide by this rule, we can actually use this formula again on our formula sheet that allows us to calculate the standard deviation. What I do is I take whatever that true proportion is, I multiply it times its complement, I divide it by its sample size, that gives me the standard deviation. So I can actually calculate the standard deviation. And I put this note here as n increases, the sigma decreases, because it's something we talk about a lot moving forward. The way I want to think about it is this. There are 33 of you in my class. Let's say I wanted to figure out the average grade of my 8th period class. If I just randomly selected one of you and used your class average to estimate the entire class, do you think there'd be some variability to what the real answer is? Like just one of you. So I just randomly grabbed one person out and said, I'm going to use you as the judge of the average for the whole class. In this case, there's some variability to it. Now, but let me ask you the following. I know I'd violate independence, but imagine I took 10 of you and averaged the 10 of you. How far do you think I'd be from the real average if I did an average of 10 of you compared to 1? Would I be closer or farther from the average if I increased the number of people I was adding it? And that's what this idea is. The idea is I increase my sample size, I reduce my variability. It's that I keep saying short and fat to tall and skinny. That's what I'm doing with the curve. I'm going from a curve that is going to look like that. That's a very small sample size. That might be a sample size of like 3. That's probably going to be a sample size of like 40. A lot less variability, but they're both still centered at kind of the same answer. So that's my goal. My goal is, what I want to do is I want to try and figure out that center, that spread, that mean, that standard deviation. And then the last piece is to determine the shape. That's where I need to make sure I've taken a large enough sample size that I can be sure that I'm going to have at least 10 successes and at least 10 failures, at least 10 orange ones, and at least 10 that are not orange of the Reese's Pieces. And I need to check that. And if I can check those two conditions, those two things, the successes and failures, I can now describe the shape as approximately normal. So this whole process says the following. When I look at a sampling method, I make sure it's random so I can tell you the center. I make sure it's independent so I can calculate the standard deviation. I check the successes and failures so that what I can do is I can determine if it's approximately normal. And if I meet all those conditions, what happens is I get a distribution that looks like this. It's normally distributed, centered at the true proportion with a calculable standard deviation, something I can calculate. What's really nice about that is then I can go ahead and I can draw that curve like we did back in chapter 2. I can go ahead and put that P in the center. I can actually calculate what all 3 of these little hash marks are. I can use normal CDF. I can use table A, either one, the z-score thing some of you use, and I can calculate areas under that curve and I can answer questions. So that's the whole idea of what we're doing with the sampling distribution. That was what we talked about last week with Reese's Pieces. So I wanted to go over that one more time to make sure you kind of had that, because I know some people were confused on what we did last time. What I need you to understand, what we did last time is the following. This is one sample. What I'm now going to talk about is I'm going to talk about 2 samples. So what's going to happen is instead of just doing this whole process once, I'm going to do this whole process twice. I'm going to check random for the sample 1. I'm going to check independent for sample 1. I'm going to check the normal for random sample 1. I'm going to check random for sample 2, independent for sample 2, normal for sample 2. And if I hit all those conditions, I now have 2 distributions where I've confirmed everything, and now I can actually do something like this normal down at the bottom. And before we dive into it, let me ask one question from before. Like, let's say I told you I have a distribution A, that had a mean of 10 and a standard deviation of 3. And I had a distribution B that had a mean of 7 and a standard deviation of 2. If I were to ask you, what is the mean of A minus B? What's the mean of A minus B? What's the difference? And Alexa, you got that just by 10 minus 7. We just did it. We did mean A minus mean B. We did 10 minus 7. It's 3. What about when I did standard deviation of A minus B? Is it 1? Can I just do 3 minus 2? It's 1, and then I'm all done? Nope. Remember, standard deviations got more work. I needed to turn the first standard deviation into a variance. I needed to turn the second standard deviation into a variance. I always add them, and then I take the square root of it. What I'm going to tell you today is the following. We're going to see what's going to happen is we're going to have a sampling distribution where we're going to have a mean of 1. We're going to have the mean of a second one. And what we're going to do is we're actually going to see what is the mean of A minus B. And I'm telling you, it's the same rule that you just did here. We can subtract them. This is equal to what we did for A minus what we did for B. Now, I'm going to tell you our standard deviation, that formula here, this guy right here, that square root P, 1 minus P over N. We're going to have that's my standard deviation of A. So this is my standard deviation of A. This is going to be my standard deviation of B. Again, we're just plugging and chugging using the formula from the formula sheet. So this is, again, if this was one sample and it was just A, that's what we'd have. If this was one sample and it was just B, this is what we have. But now what I'm going to say is I want to take that standard deviation of A. I want to go ahead and I want to do the standard deviation of A minus B. I want to subtract these two standard deviations. Well, I'm telling you, again, we can't just say 3 minus 2 is 1. We have to process it this way. We have to take that one standard deviation. We have to take the second standard deviation. Well, as you notice, this is already standard deviation. This guy's got a radical in it. What that's telling me is that this thing under here, under the radical, these two things under the radical are variances, actually. That's what they really are. The square root is what turns them into standard deviation. Standard deviation always comes from the square root. So what I need to do is I need to do the following. To combine the two, I am going to take the first variance. I am going to take the second variance. I am going to always add them, and then the square root brings us back. This is how I combine two standard deviations. I add both of them under the radical, and I square root it to come back to it. Again, on the formula sheet. This is on the formula sheet. So we're going to use that formula in a moment. So let me show you the example I want to talk about. Here's the example I want to talk about. Among randomly selected teens aged 15 to 17, 57% of 248 boys surveyed had posted an online profile. 70% of 256 girls surveyed had posted an online profile. Let's talk about the center, shape, and spread of their difference. So what I need to do is the following. I need to do that center, shape, spread check for boys and for girls. So the center check was always based on random. So let me ask you, was this process random? And the reason it was random, the word random appears in the problem. That is where you're going to see it. Now, if you don't see the word, it's something where you'd have to say, hey, it doesn't say random in here, so therefore I question whether this is unbiased. But since this says random, what I can now do is the following. I can now say the following. Boys are randomly selected, so it's an unbiased estimator. The center of boys is going to be the 57%. I don't know any better, so I'm just going to say the boys are where I got it at 57%. Girls were also randomly selected, so I have an unbiased estimator. So again, I'm going to assume that sample I got, that 70%, that's going to be the center of my distribution. I've done the sample one time. Now, again, in the real world, we're not just going to stop at one. In the real world, you would do the sample multiple times. I would talk to 248 boys, random samples of 248 boys multiple times, and I kind of build that little dot poster we have up in the classroom for Reese's Pieces. I would do that. But in this case, we're just going to go, okay, we don't know any better. We're just going to use that one sample as our best guess. We're going to use that one sample of girls as our best guess. So now what I have is I have boys and I have girls. I have the center of the boys distribution at 57%. I have the center of the girls distribution at 70%. So I've checked those first two conditions. Any questions on the center check on the random? Next, let's check spread. Spread is going to be the standard deviation. Spread is going to be the independence check. Spread is going to be the 10N check. So my boys are 248 in the sample. 10 times 248 gives me 2,480. Do you think it's safe to assume there are more than 2,480 boys online aged 15 to 17? Yeah, absolutely. Yeah. So, and if you look at with girls, same idea, 10 times 256, 2,560. I feel pretty good saying there's probably more than 2,560 girls aged 15 to 17 online. So what that means is the following. I've checked these. I made those safe to assumes about that independence. Now what I can actually do is I can calculate each one of their standard deviations. What I can do for the boys is the following. I can go ahead for the boys and I can plug in the numbers. 57, 1 minus 50.57 over 248. I can find out that the boys' standard deviation is a little over 3%. I can do the same thing for girls. I can figure out that the girls' standard deviation is going to be about 2.86%. So now what I know is, I know where the boys are centered. I know how much variability there are to the boys. I can go to the right on the number line. I know where the girls are centered. I know where the variability to the girls are. Next and last is I can determine the shapes. And the shape is the 10 or more successes, the 10 or more failures. And again, if you think about it, it doesn't say how many successes explicitly or how many failures, but you can calculate it. 57% of the 248 have an online profile. So what does that mean? 248 times 57.57 tells me that 141.36. I would expect, I had about a little over 141 boys who said, yes, I have an online profile. The rest are the ones who don't have an online profile. That was 106, a little over. Both of those numbers exceed 10. So what that tells me is that boys' distribution is approximately normal. What I now know is the following. I have a sampling distribution for boys that's centered at 57% with a standard deviation of a little over 3%. So I could go ahead and I can draw myself a curve. I could put those little standard deviations down. And what I could do is I could make an estimate of like how surprised I'd be if I got a certain number of boys versus this. So let me ask you, would you be surprised if I pulled the sample based on this? Let's say that this was in fact true. Would you be surprised if I ended up with 60% of boys with an online profile? Would 60% be a stunning number to you? And why not? Why is 60% not surprising? How many standard deviations is 60% away from 57? It's 1. About 1. That's not surprising to me. Now, would you be stunned if I ended up with 82% of boys with an online profile? 82% on this case. 82% says 82 minus 57 is 25. 82 minus 57, 25. 25 divided by 3 is like what? 8? That's 8 standard deviations away. What's the most standard deviations we expect in a normal world? What's the most we really? 3. 3 is really it. Anything bigger than 3, we're like, whoa, something's going on. That's really unusual. So that's for boys. Well, I just did the same process for girls. I came up with the same idea, centered at 70, standard deviation at 2.8, approximately normal. They met the success and failures. So now I have a girl's distribution centered at 70, has about 2.8 on each standard deviation, and it's approximately normal. So now I can answer questions about girls. Here's the deal. I am not so interested in boys alone or girls alone. I'm interested in the difference between boys and girls. I'm interested in what is the difference between those two proportions. So if I were to ask you, what is the difference between, if I were to say this, what is the difference between the proportion of boys minus the proportion of girls? What is the difference between the proportion of boys minus the proportion of girls? Yep. It is going to be boys are 57%, girls are 70%. I subtract them. I end up with negative 13%. So I would expect that on average, it would be centered at about negative 13. So what I'm saying is I would imagine that the center of this distribution is going to be centered at about negative 0.13. Now, the challenging part and the part that you'll get more comfortable with the more problems you do like this is how I combine these two standard deviations. I'm not just going to do 3.1 plus 2.8. I'm not just going to say, or I'm not going to do 3.1 minus 2.8. What I need to do is I need to do the following to get their standard deviation. I need to use this formula right here, again, on your formula sheet. This formula is on your formula sheet. You do not need to memorize it. It is right here for you to use. I plug in the numbers. I pick up my calculator. My calculator tells me that the combined standard deviation is about 4.25%. It's larger. Remember when I talked back before winter break, it's larger than either one of the standard deviations. And I'm going to tell you that's always going to be the case. When I go and look for the difference, it's always going to be larger than whatever the bigger one of the two is. So the big one is 3%. When I combine them, it's going to be larger. So in this case, it's 4.2%. And the end part is, this is the easiest check to do. If one distribution shape is normal and the other distribution shape is normal, their difference is normal. So now what I have is the following. I have taken two distinctly different distributions. They would have two different little, bell-shaped curves. I've combined them into one. Instead of having two curves, one centered at 57, one centered at 70, with similar but different standard deviations, I now have a one distribution that is normal, centered at 13%, with a standard deviation of 4%, boys minus girls. And if I had done this as girls minus boys, it literally would have been centered at positive 13% with the exact same standard deviation. That's it. And the reason that this is important is I'm going to show you what this curve looks like. That's what boys versus girls looks like. It looks like that. It is centered at 13%. I added 4.25. I subtracted 4.25 to the left. I want you to look at this curve and I want you to see something that should stand out to you. If I were to ask you, based on the sample that I just did, would you be surprised if more boys had an online profile than girls? Would you be surprised if more boys had an online profile than girls? What would it mean if boys had more online than girls? What would it mean about the difference of their proportion? What kind of number would it be if boys minus girls, if boys had more online than girls? It'd be positive. Look at that curve for me. What do you notice about that curve? Look at these numbers right down here at the bottom. What do you notice about those? It's all negative. 0 is out here somewhere. 0 is going to be like out here. That's a surprising result to me. What that would tell me is the following. If, let's say that when I did this, for some reason, I came up with the perfect method to determine this answer. And in the real world, it actually is 57% of boys with online, 70% of girls with online. Let's say that, for some reason, I got incredibly lucky the first time. You're going to go out and you're going to do the same process, and you ended up with a positive number, more boys than girls. What that would tell me is, hey, something's going on at the school that I might want to look into. Why do boys have more on? Why do boys have more of an online profile than girls here? What's going on here? Is there something distinct here that I need to analyze? Or the other way to think about it is this. I come to you as the researcher. I come to you as the person who's supposed to be the expert. And I say to you, okay, boys are online with a proportion of 57%. About 50% of boys 15 to 17 are online. And I believe, based on my research, that 70% of girls age 15 to 17 are online. That's what my belief is. And you're like, okay, well, let's see how good your work is. I'm going to go grab myself a random sample. And the random sample I'm going to grab says the proportion of boys is 61%. The proportion of girls is 68%. So what's the difference between boys and girls here? What's the difference between boys and girls here and the sample that you would have gone out and pulled? 61% boys, negative 0.7, negative, yeah, so it's negative 0.07, right? Where would that fall on my little curve? Like right about here. Is that a surprising result to you if I'm here? Nope. Nope. So what that says is, hey, yeah, maybe you're telling the truth. But let's say instead, when you went out and did this, you ended up with this. 80% boys, 68% girls. You just ended up with a difference of 12% positive. 12% positive is way off this line. You now have evidence to come back to me as the subject matter expert and tell me the following. I don't buy what you're selling. You told me 57% of boys are online and 70% of girls are online. So you know what I did? I came up with this curve. This is what I should have seen when I pulled my sample. I ended up way out here. I should not have been all the way out there if what you were telling me is true. That's where the kind of thing we're going to be looking at. Is that somebody's going to make a claim, they're going to stake a claim to something. We're going to grant them whatever they said. I'm going to say, okay, whatever you're saying, I'm going to assume it's true. I'm going to draw myself a curve. I'm going to say that based on your claim, this is what I should have. And now what I'm going to do is I'm going to follow your process that you told me. I'm going to go get a samples of the same size. I'm going to determine my answers. I'm going to see where I fall on this curve. And wherever I fall on this curve is going to give me evidence to either thumbs up or thumbs down on whether your claim is to be believed. Okay. So here's the deal. Hopefully that helped. If some people were confused from last time, I'm hoping that helped. What I'd recommend you do is the following. In that same virtual folder, there is a practice in there that is exactly like this. And what I would suggest you do is you try it. You're going to do 2 different samples. You're going to do random, independent, normal check on both. You're going to use the rules to combine them. I have the answer key there. And right as soon as class is done, what I'm actually going to do is I'm going to go back and I am going to add the video that has the explained answer there for you so that you can look at it as well. So what I'd ask is you try and give this a chance, give this a practice. Let me know how you feel. When we come back together again next Wednesday, we're going to do this stuff for means.